Transformations of the exponential function. So let's review some transformations that we know from the past. If you're given y equals f of x, describe in words the transformations that occur to the graph of y equals negative 2 f of 2x plus 4 minus 3. Now remember that when you are describing transformations, and it does tell you to describe it in words, that you want to make sure that the horizontal transformations are in factored form. So first thing I did is factor it, and now we can look at the different transformations. The first transformation that I see is a vertical reflection in the x-axis. Second one is a vertical stretch by a factor of 2. Then we have a horizontal compression by a factor of a half, a horizontal shift to the left 2 units, and a vertical shift down 3 units. Question number 2 says, write the mapping formula for the function. So it's the same function that we're looking at as the first question. So first thing I did is factor it out. And so if I have x and y as my initial points, with your mapping formula, all you're trying to do is figure out where your x values are going to and where your y values are going to. Normally we look at this in a table. So normally we have x and y, and then we do the mapping formula, and then we have our new formulas up here. But if you write it as a point, it means the same thing. Okay? So horizontally what's happening is that the graph is being compressed by a factor of a half, and then shifted to the left 2. And vertically what's happening is the graph is being reflected, stretched, and then shifted down 3 units. So this is our mapping formula here. Okay, so 1 half x minus 2, and then the y value is negative 2y minus 3. Okay, so let's look at some things that we already know about exponential functions. First of all, the exponential functions are written in the form y equals b to the exponent x. And depending on whether the base of the function is greater than 1 or if it's between 0 and 1, the direction that the graph goes changes. So if the base is greater than 1, you get a graph that's increasing. So as you move from left to right, the graph is increasing exponentially. But if you have a base between 0 and 1, what happens is the graph is decreasing exponentially. So initially it's decreasing really fast, and then it starts to slow down, or it's increasing really slowly, and then it starts to increase much faster. Okay. Okay, some review of the transformations that you know. A still represents the vertical stretch or compression. If it's negative, it represents a reflection in the x-axis. K is still your horizontal stretch or compression. If it's negative, it's a reflection in the y-axis. D is your horizontal translation, so shifting the graph left or right. And C is your vertical translation, shifting the graph up or down. Quick note, vertical transformations are outside the brackets, so that would be A and C, and horizontal transformations are inside the brackets, so that would be K and D. The order of transformations is important. You want to make sure that you do the steps that require multiplication, like stretching and reflecting first, and then translating the graph next. Okay, so that's the adding and subtracting part. And because we've already looked at exponential functions and we know that there is a horizontal asymptote, remember that vertical shifts affect horizontal asymptotes. So if you have a horizontal asymptote, as you move the graph up or down, the location of the horizontal asymptote changes with it. Okay, transformations of any function. So this is the last time you're going to look at all these transformations. The effects of each transformation are still the same. In other words, A, K, D, and C affect the base graph in the same way. So here's the one with any base function, so we don't know what f represents. The first one, or the second example here is for a quadratic function, so f gets replaced with an exponent of 2. Notice the location of the values, so A, K, D, and C. It still affects the base graph, which was quadratic in this case, in the exact same way. Here's the root function with all the transformations, the rational function with all the transformations, and finally the exponential function with all of its transformations as well. And what you should notice is that because the variable x is in the exponent, for exponential functions, all the horizontal transformations are part of the exponent. So you'll notice a little k and a little d in the exponent. That's where you'll find the horizontal transformations. A and C, as usual, will be at the beginning and at the end, and those represent your vertical transformations. B, which is the base of the function, is the one part that makes an exponential function a little bit more unique. So we're going to look at how to graph these in a few minutes. Okay, so to graph an exponential function in the form y equals a times b to the exponent k x minus d plus c. The first thing we need to do is determine what the base graph is. So what you want to do is look at the equation and try to figure out what the base value is that has the exponent applied to it. And that'll tell you there what the base function would be. Okay, y equals b to exponent x. Once you figure out what the base graph is, what you want to do is try to come up with some key points for the base graph. Okay, so here I've chosen some simple values of x, and what that'll show me is what's happening to the left and on the y-axis and then to the right. Okay, so those 3 points are sufficient to sort of get the shape of the graph going. Okay, so once you've chosen these x values, your next step is to substitute it into the base graph formula, and you try to solve for the corresponding y values. Once you know those, what you can do is either use the mapping formulas to create your new points, or you can try to come up with a new asymptote. Now remember what we said earlier, the asymptote changes depending on whether you shift the graph up or down. So the c value here will tell you what the horizontal asymptote is. Okay, so you want to graph the horizontal asymptote, you want to come up with your formula, you want to come up with your mapping formula and the key points for your new graph, and then graph the asymptote and graph the new transform function as well. So we'll look at a couple of examples. So here's the first one. So for the following exponential function, the first step is to sketch the function. So what I need to figure out first is what the base graph is equal to. So that's my first step. So the base graph in this case, what I'm looking for is where the exponent is and what the value is as the base that has that exponent raised to it. So 2 is actually the base. So 2 to exponent x, y equals 2 to exponent x is actually your base function. Okay? That's the only time you're going to use the value 2. That represents your base graph. Okay? In terms of your horizontal asymptote, which is my next step, okay, your horizontal asymptote is the shift up or down. And so because the graph is shifted down 4 units, I know the horizontal asymptote is y equals -4. And so what I can actually do is sort of sketch this right away. Remember, horizontal asymptotes are graphed using a dashed line. So this is y equals -4. And now I'm expecting the graph to be up here somewhere. And I know it's going to be up here somewhere because the only way to get a graph down here is if you reflect it vertically. And there's no vertical reflection, so I'm expecting my graph to be above the asymptote. So now what I'm going to do is I'm going to try to come up with key points for the base graph. So x and y equals 2 to the exponent x. And so I'm going to choose my simple values for x, so -1, 0, and 1. And I'm going to plug it into the base function, and this will just give me the key points for this particular base graph. And now, because it's an exponential function, your base function can change. So we have to look at it based on this particular example. So I'm going to substitute this in. I get 2 to exponent -1, which is 1/2. And then 2 to exponent 0 is 1, and 2 to exponent 1 is 2. Now I'm going to come up with my mapping formula and try to create the new points that I need so that I can actually graph them. So horizontally, I'm going to look at the exponent to see what's happening horizontally to the function. And the only transformation is a shift to the right. So my mapping formula would be x plus 1. Vertically, I'm going to look at the values before the base graph and after the base graph. So there's a vertical stretch by a factor of 3 and a vertical shift down 4 units. And now I'm going to create my new points by substituting them the original x and y values into the formulas. -1 plus 1 is 0, 0 plus 1 is 1, 1 plus 1 is 2. 1/2 times 3 is 1.5, minus 4 is -2.5. 3 times 1 is 3, minus 4 is -1, and 3 times 2 is 6, minus 4 is 2. I'm going to plot these points. So I have a point at 0 and -2.5. I have a point at 1 and -1. And I have a point at 2 and 2. Okay, and so what you'll notice is 3 points here. And what I want you to recognize is when you are sketching your exponential function, the point closest to the asymptote is the point that's sort of approaching the asymptote. So that's how I know that the graph is going to go down and towards the left that way. And the point farthest away from the asymptote continues to get farther and farther away from the asymptote as well. So here's a graph of y equals 3 times 2 to the exponent x minus 1 minus 4. Now then, all we need to do is state the domain. So that's all real numbers since the graph continues infinitely to the left and to the right. The range has some restrictions on it. So we have y as an element of all real numbers such that the smallest value of y that we have is just above -4. So -4 is the barrier. So y has to be greater than -4. Equation of the asymptote is y equals -4, and as you can see, as we move from left to right, the graph is actually increasing. So as you move from left to right, you're going from smaller numbers to higher numbers. So the function is actually increasing in this case. Okay, we're going to look at one more example. It'll be slightly different. So for example 2, for the following exponential function, again, we're going to sketch, state the domain, range, and equation of the asymptote, and then talk about whether the function is increasing or decreasing. Okay, so the first step is to figure out what the base function is. And so I'm going to look at where my exponent is, and whatever the base value is to that exponent, that's going to represent my base function. So 1/2 is my base function. So what I'm going to do is I'm just going to go over this just to help you recognize that that 1/2 is actually part of your base function. You're never going to use that towards your transformations. That just tells you that this is the original function that we're looking at. So that's a special thing about exponential functions. The base function can be different. Okay, whereas quadratic, it's always x squared. Root, it's always square root of x. But for exponential, you can have 2 to the exponent x, 1/2 to the exponent x, 3 to the exponent x. The base function can change. Okay, so that's your first step, recognizing what the base function is. Next thing I'm going to do is figure out the horizontal asymptote. So I'm going to look at whether the graph has been shifted up or down. And I can see that the graph has been shifted up 2 units. So that's the horizontal asymptote. And then from here, what I'm going to do is create my base points. And so my x values I'm going to choose are -1, 0, and 1. Substitute that into the base function. So 1/2 to the exponent -1 is 2. 1/2 to exponent 0 is 1, and 1/2 to exponent 1 is 1/2. And then I'm going to create my mapping formulas and then go from there. Before I actually create my mapping formulas, what I'm going to do is draw the horizontal asymptote. So at y equals 2, I have my horizontal asymptote. Now in this case, I'm expecting all my points to be below the asymptote, and the reason for that is because the graph has been vertically reflected. So I'm expecting the graph to be down here somewhere. So let's look at our horizontal transformations. I only have a horizontal shift to the left 3, so this is x minus 3. No other transformations in the exponent. And then in terms of my vertical transformations, I'm looking before the base function and after it. So vertical reflection, stretch, and a shift up 2 units. So apply these values to your key points. So -1 minus 3 is -4, 0 minus 3 is -3, 1 minus 3 is -2. And then -3 times 2 is -6 plus 2 is -4. -3 times 1 is -3 plus 2 is -1. And -3 times 1/2 is -1.5 plus 2 is 0.5. And then I can plot these points, and if my points don't appear below the asymptote, then I must have done something wrong. But if they do, then most likely your work is correct. And you'll notice again, you have one point that's very close to the asymptote. That tells me that that part of the graph is approaching the asymptote. Then you'll have the another point that's far away from the asymptote. That tells me the graph continues to be farther away from the asymptote there. So there's the function y equals -3 times 1/2 to the exponent x plus 3 and then plus 2. Now the domain for this, again, the graph goes infinitely to the left and right. So it's x is an element of all real numbers. The range, because the graph is below the asymptote, it's an element of all real numbers, but y has to be less than whatever the asymptote's equal to, so y is less than 2. And then the equation of the asymptote we know is y equals 2. And in this graph, although the base is between 0 and 1, I know you would normally expect the graph to be decreasing, but because the graph was reflected, what it ended up doing is making the graph increase instead. So this graph is also increasing like our previous example. Okay, in the next video we'll have all the conclusions in it.